Hey guys, here is section 7.2, day 2 notes. So on the first day of day 2, I showed you how the inverse secant and the inverse cosecant functions are going to work. So now we have to figure out how the inverse cotangent function is going to work. And he's a little bit harder than the other two, and you'll see why. All right, well, first of all, here's the graph of the cotangent function, right? So he's clearly not a one-to-one function, and he should not have an inverse, right? So if you look at the way his graph behaves, if I plug an angle between 0 and pi over 2 in, a ratio between 0 and infinity comes out. So these are your quadrant 1 angles and ratios, right? If I plug an angle between pi over 2 and pi in, a ratio between 0 and negative infinity comes out. So these are your quadrant 2 angles and ratios. If I plug an angle between pi and 3 pi over 2 in, now a ratio between 0 and infinity comes out. So these are your quadrant 3 angles and ratios. And then last, if I plug an angle between 3 pi over 2 and 2 pi in, a ratio between 0 and negative infinity comes out. So these are your quadrant 4 angles and ratios. And then they'll just start to repeat over and over and over again, right? And I can even go back way this way. And then just remember, he has asymptotes. So when I plug a angle of 0 radians in, an undefined ratio came out. When I plugged an angle of pi radians in, an undefined ratio came out. When I plug an angle of 2 pi radians in, an undefined ratio came out, right? Okay, so like I said, this is clearly not a one-to-one function. So we want to see, well, what portion of his graph do we keep to make his inverse exist, right? What part of the graph survives the cut? So if you start right here at 0, a great place to start on all of them. If I go on this leg of the graph, is it passing the HLT? Well, yeah. And then I can keep going even onto this leg of the graph, and it continues to pass the HLT. So this entire section on his graph passes the HLT. But the minute I try to include another leg of the next cycle, it won't pass the HLT anymore. And even if I go backwards, it still won't pass the HLT. So the only portion of his graph that we're going to be able to keep to make his inverse exist is his first cycle, if you will. Okay, so right there, that's the portion of the graph that we're going to keep to make the inverse exist. Okay, so if you notice, on the leg of the graph that we keep on that cycle, only quadrant 1 and quadrant 2 angles survive the cut of his graph. So the inverse cotangent is only going to be capable of spitting out quadrant 1 and quadrant 2 angles. Because again, those are the only angles that survive the cut of his graph. Okay? All right, so let me just list out a couple points that survived the cut. Let me keep this up here, I guess. All right, so if you notice, the point 0 undefined survived. Okay. The point pi over 4, 1 survived. All right. The point pi over 2, 0 survived the cut of his graph. Okay. The point 3 pi over 4, this is negative 1 right here. 3 pi over 4, negative 1 survived the cut of his graph. And then last, the point pi undefined survived the cut of his graph. So if these are all points that survived the cut of his graph, then all of these points in reverse will make up the graph of his inverse, right? So now his inverse is going to look like this. So the inverse cotangent graph, well, now ratios, well, if you notice, ratios from infinity to negative infinity survived the cut of his graph. So all ratios survived the cut. So ratios from infinity to negative infinity survived the cut of his graph. But only angles from 0 to pi survived the cut of his graph. So only angles from 0 to pi will be able to come out of his function, okay? So notice if you have an asymptote at 0, 0, a VA, then you're going to have an HA at 0, 0. Okay, and then if he's got a VA at pi 0, well then at 0 pi, he's going to have an HA. Okay, and then last, so that's 0 undefined. That in reverse gets us this one. All right, now pi over 4, 1. So now when 1 goes in, an angle of pi over 4 radians comes out. Okay, pi over 2, 0. So now when 0 goes in, pi over 2 comes out. So now that's a point on the inverse. And now when negative 1 goes in, when a ratio of negative 1 goes into the graph, or into the function, now an angle of 3 pi over 4 radians comes out. And then last, when undefined goes in, well, again, a ratio you can't plug in, then pi radians comes out. That's not going to be an angle he's going to be able to spit out. It's going to take an undefined ratio to get that angle out. So he's not going to be an angle that can come out of this function. Because again, it will take an undefined ratio to make that angle come out. I can't plug an undefined ratio in, so pi will be an angle he is incapable of spitting out. So when I try to picture his graph, when I go from this dot to this dot to this dot, and then it's going to hug that asymptote. And then it's going to go from this dot to this dot to this dot and then hug that asymptote. So this is what the inverse cotangent graph is going to look like, right? He has ratios going into him as his domain from negative infinity to infinity. But his range, the angles that are coming out of him are only going to be from 0 to pi. But it won't be 0 and it won't be pi. We cannot include them as angles he can spit out because it's going to take undefined ratios to make the angle of 0 radians or the angle of pi radians to come out. And you can't plug an undefined ratio in. So only angles from 0 to pi will come out, but not including 0 or pi. Okay? All right, so look what his graph is telling us. It is showing us that when you plug a ratio bigger than 0 in, if I plug a ratio greater than 0 in, then an angle between 0 and pi over 2 comes out. And those will be angles that are found in quadrant 1. So if you have a ratio that is bigger than 1, then you're going to want to put that angle in quadrant 1. Okay? His graph is also showing us that if I plug a ratio less than 0 in, if I plug a ratio less than 0 in, then an angle between pi over 2 and pi comes out of that function. So an angle between pi over 2 and pi comes out of that function. So that's going to be an angle that is found in quadrant 2, right? Because quadrant 1 and quadrant 2 are the angles that survive the cut of his graph. So if you take the inverse cotangent of a ratio less than 0, you're going to get an angle that's in quadrant 2. And that's where you should put that angle or that triangle if you need to draw a picture of it. Okay? All right, so that's how the inverse cotangent works. He's only going to be capable of spitting out angles between 0 and 180 degrees, or 0 and pi radians, right? Quadrant 1 and quadrant 2 angles are the only angles that come out of the inverse cotangent, which is why he's different. Because if you remember, the tangent, which is his reciprocal trig function, the inverse tangent only spit out angles between quadrant 1 and quadrant 4. He spits out angles between quadrant 1 and quadrant 2. So they're reciprocals, but their inverses don't behave like one another. They spit out different angles, all right? All right, so here we go. Here's our cheat chart. We saw that if you take the inverse secant, the inverse cosecant, or now the inverse cotangent of a positive ratio, then they're all going to spit out angles in quadrant 1. If you take the inverse secant, cosecant, or cotangent of a positive ratio, they all spit out a quadrant 1 angle, right? Now remember, the secant and the cosecant, their inverses, you have to plug ratios that are bigger than 1 or less than negative 1 into them, right? Those are the ratios that survive the cut of their graph. But the inverse cotangent, he has no bad ratios. So you can plug any positive ratio in and you'll be fine. It'll be a quadrant 1 angle. All right, we saw though that the inverse cosecant behaves just like his reciprocal inverse, the inverse sine. And when you take the inverse cosecant of a negative ratio, it will spit out an angle in quadrant 4, just like the inverse sine, right? But, and the inverse secant, if you take the inverse secant of a negative ratio, he spits out an angle in quadrant 2, just like his reciprocal trig function, the inverse cosine, right? He spits out angles in quadrant 1 or quadrant 2. Okay, but the inverse cotangent, right? The inverse cotangent will spit out an angle in quadrant 1 if you take the inverse cotangent of a positive ratio. And then he'll spit out a quadrant 2 angle if you take the inverse cotangent of a negative ratio. So that's different because the inverse tangent of a negative ratio spit out an angle in quadrant 4. So they're reciprocals, but their inverses don't behave like one another. So the inverse cotangent actually behaves like the inverse secant, which is the reciprocal of cosine. And that is solely just because of the angles that we were able to keep that survived the cut of their graph. Okay, that is the only reason why. Okay, so here we go. The inverse secant, right? He spits out angles in quadrant 1 and quadrant 2 between 0 and pi radians. That's how he behaves. All right, the inverse cosecant. He spits out angles in quadrant 1 or quadrant 4, right? Just like his reciprocal, the inverse sine. Just like the inverse sine, right? And let's go back. The inverse secant spits out angles in quadrant 1 and quadrant 2, just like his reciprocal, the inverse cosine. Okay, now the inverse cotangent, though, will only spit out angles in quadrant 1 or quadrant 2. Okay, angles between 0 and pi. I should have labeled this. Okay, so actually, he doesn't behave like the inverse tangent. The inverse tangent did this, quadrant 1 or quadrant 4. The inverse cotangent actually behaves like the original function inverse cosine. And again, that's going to be important because we already know there's no secant, cosecant, or cotangent button on the calculator, right? If you wanted to take the secant of some angle, you had to rewrite that as 1 over the cosine of some angle, right? You weren't able to find a secant button on your calculator. But here's the thing. If you have the inverse secant of, oh, let me get that a little bit neater, sorry. If you have the inverse secant of some angle, you're not allowed to rewrite that as just 1 over the inverse cosine of that angle. The translation is just not the same. They're not equal like that when you use the calculator. So the inverse secant is going to have to be turned into a full-on cosine ratio, okay? So the inverse cosecant is going to have to be turned into a completely sine ratio. But since the inverse cotangent behaves like the inverse cosine, you're not going to turn an inverse cotangent problem into a tangent problem because they don't behave the same way. You're actually going to turn your inverse cotangents into cosine ratios. So you can use the inverse cosine because that's the one he behaves like, all right? So that's going to be the trickiest one. These ones will just go to their reciprocals, but these ones can't. The inverse cotangent actually has to become an inverse cosine problem because that's who he behaves like. All right. So, just to kind of put that in writing. Therefore, the inverse secant function has the same range, and by range we mean it spits out the same angles.
Outfit challenge. Your parents pick the color of your favorite food.
Okay, the inverse secant spits out the same angles as the inverse cosine function. Right? They spit out angles between quadrant 1 and quadrant 2. The inverse cosecant function has the same range, which means he spits out the same angles as the inverse sine, because they both spit out angles in quadrant 1 and quadrant 4, so their behavior is the same. But the inverse cotangent function has the same range. He spits out the same angles as the inverse, not the tangent, remember? The inverse tangent spit out angles in 1 and 4, but the inverse cotangent spits out angles in 1 and 2. Just like the inverse cosine function. All right, so it's because of that behavior, because the inverse cotangent acts just like the inverse cosine, you're going to turn inverse cotangent function problems not into tangent problems, not into inverse tangent problems, but into inverse cosine functions or problems, okay? All right, The calculator does not have an inverse secant, cosecant, or cotangent button. So when using a calculator to approximate the value of an inverse reciprocal trigonometric function, to approximate an inverse secant, cosecant, or tangent, you must convert or rewrite it as one of the main inverse trigonometric functions whose range is the same. All right, so if you're going to do an inverse secant, his range is just like the inverse cosine. So you're going to convert this to an inverse cosine problem. Great, no big deal, right? They're reciprocals of each other anyway. All right, the inverse cosecant function, he spits out the same angles as the inverse sine. So you're going to convert them to inverse sine problems, which is great because they're reciprocals of each other anyway. So that'll be easy. But the inverse cotangent, he spits out angles just like the inverse cosine. So you're going to have to convert inverse cotangent problems into inverse cosine problems. You will not turn these into inverse tangent problems because the inverse cotangent and the inverse tangent do not spit out angles in the same quadrants. They don't behave the same way. So you're going to have to turn inverse cotangent problems into inverse cosine problems, okay? All right, here we go. So it says, use a calculator to approximate each expression in radians rounded to 2 decimal places. So you're gonna, for the most part, be using your calculator once you get yourself set up. So I have my calculator. Now they want our angles in radians. So go to mode, oh, turn it on. Go to mode and make sure you are in radian measurement, not degree. You wanna make sure you are in radians, not degrees, because they are asking for radian measurements of all these angles. All right, here we go. So I'm in radians, I'm ready to go. So what if they asked you what is the inverse secant of 3, right? What is the inverse secant of this ratio? What is the angle that is the answer to this question? Because that's what inverse trig functions get us. They get us angles, right? Well, the problem is there's no inverse secant button on my calculator. I have inverse tangent, inverse cosine, and inverse sine. And like I said, I cannot do this as 1 over the inverse cosine. The translation is just not the same, and it doesn't get you the right answer. So what you're going to have to do is turn this into inverse secant spits out the same angles as the inverse cosine, right? So we're going to convert this to an inverse cosine problem because there's an inverse cosine button that I'm going to be able to use. All right, so remember this. The inverse secant, just like the inverse cosine, spits out angles between 0 and pi, quadrant 1 and quadrant 2 angles. We already know that if you take the inverse secant of a positive ratio, it's going to spit out a quadrant 1 angle. We've already learned this, all right? The answer to this is some quadrant 1 angle. But what quadrant 1 angle? All right, well, what this is saying is that the secant of some quadrant 1 angle has a ratio that is equal to 3. That is what this problem is saying. The secant of some quadrant 1 angle has a ratio of 3. Well, let's convert this to a cosine ratio. So then the cosine of this quadrant 1 angle would equal a ratio that is the reciprocal of 3. What is the reciprocal of 3? 1/3. So you have turned this into a cosine ratio. So now all you need to do to figure out what angle it is take the inverse cosine of this ratio. So the answer is, what is the inverse cosine of this ratio? And then that will get us the quadrant 1 angle that we know is the answer to this. So now just ask your calculator, what is the inverse cosine of 1/3? And hit enter. And it is about 1.23 radians. That is the angle that has a cosine ratio or a secant ratio of 3. And I'm going to label it radians so you know. So we know the answer is an angle that is 1.23 radians big. And again, if you're wondering, well, is 1.23 radians a quadrant 1 angle? Well, remember, this is 0 radians. This is pi over 2 radians. Pi divided by 2, 3.14 divided by 2 is about 1.57 radians. So where's 1.23 radians? Right somewhere in between those two. So it's a quadrant 1 angle for sure. Okay? So again, you're going to turn this inverse secant problem into an inverse cosine problem. So all you're going to do, instead of taking the inverse secant of this ratio, you take the inverse cosine of his reciprocal, and that's going to get you your angle. Okay, look at this one. The inverse cosecant of -4. Okay, well, we know that the inverse cosecant just like the inverse sine, spits out angles between 1 and 4, quadrant 1 and quadrant 4. We know if you take the inverse cosecant of a negative ratio, the answer is some quadrant 4 angle. We know the answer to this is a quadrant 4 angle. So what the problem is really saying is the cosecant of what quadrant 4 angle equals a ratio of -4, right? So let's turn this into the original trig function that he behaves just like, which is the inverse sine. So then if the cosecant of this angle is -1/4, then the sine of that quadrant 4 angle would equal a ratio that is his reciprocal, which is -1/4. So to figure out what angle this is, now I can take the inverse sine of that ratio. So what is the inverse sine of -1/4? And it's going to equal some quadrant 4 angle. Let's see what it is. So ask your calculator, because again, that's not a special ratio. That's not 1/2 or √3/2 or √2/2. That's not one of our 30s, 60s, 45s, or some multiple of them. This is just some random angle. So we have to use our calculator for this because it's not a special ratio. So what is the inverse sine of -1/4? Hit enter, and it is about -0.25 radians. It is an angle that is about -0.25 radians. All right, and if you're wondering, well, is that an angle in quadrant 4? Well, think about it. Here's 0 radians. Here's -π/2 radians, which is -1.57 radians. -0.25 is somewhere in between them. It's an angle in quadrant 4. Okay, well, here we go. Let's look at this one. The inverse cosecant of 0.8, right? So we know if you take the inverse cosecant of a positive ratio, he's only capable of spitting out angles in quadrant 1 and quadrant 4, right? And if you take the inverse cosecant of a positive ratio, it should be a quadrant 1 angle. The answer to this should be a quadrant 1 angle. Now, there's a problem with this one, and I don't know if you're going to catch it. Luckily, your calculator will if you don't. So I'm just going to keep going and show you what's about to happen. All right, so let's say you say, all right, the answer to this is some quadrant 1 angle, right? So this is saying, well, 8/10. You can either leave it as 0.8/1 and just use the decimal, or you can think of it as 8/10. It's 8/10, right? Either way, it's going to figure itself out. So watch this. So what this problem is saying is that the cosecant of some quadrant 1 angle equals a ratio of 0.8/1. Okay, well then if we turn this into a sine problem, then the sine of that quadrant 1 angle would equal a ratio that is his reciprocal, 1/0.8. So then to find out what angle this is, all I have to do is take the inverse sine of that ratio. The inverse sine of 1 divided by 0.8 will get me that quadrant 1 angle, right? It should. There is a problem, but I'm just going to keep going. The inverse sine of 1 divided by 0.8. Hit enter, and it says domain error. The reason it says domain error is because of this, okay? If you look at it in its fraction form, it's 8/10, right? So this is equal to 8/10. Okay, so then that means you would have the sine of some quadrant angle has a ratio of his reciprocal, 10/8. But here's the problem. Guys, the sine ratio is O/H. Is O ever bigger than H? No. This is a ratio that is bigger than 1. And does the sine ever have a ratio that's bigger than 1? No, it does not. So now, if you try and take the inverse sine, there's no angle that has that sine ratio that's bigger than 1. So the answer to this is just undefined. There is no such angle that'll make this statement true. Okay, now again, that's the good news. If you didn't catch it, like, wait a minute, could you take the inverse cosecant of this type of ratio? If you don't catch it, your calculator will, so don't worry, okay? But this is an undefined answer because this is a ratio that the sine function or even the cosecant never would have had, right? 8/10 is a number smaller than 1. Well, if you remember, the cosecant only has ratios that are bigger than 1 or less than -1. So this is a ratio that is not defined for these functions, all right? So it's an undefined answer. But don't worry, just go with it because your calculator will catch them, okay? All right, here we go. These are the more difficult ones, the inverse cotangent, right? Okay, we know the inverse cotangent only spits out angles between quadrant 1 and quadrant 2. just like the inverse cosine. It does not behave like the inverse tangent. The inverse tangent would spit out angles between 1 and 4. So they don't act the same. Therefore, you can't turn inverse cotangents into inverse tangents because they don't spit out the same angles. So they can't become inverse tangent problems. You're going to have to turn inverse cotangent problems into inverse cosine problems because they spit out the exact same angles. They both spit out angles between 0 and pi, quadrant 1 and quadrant 2 angles. All right, but let's go with this. All right, so the inverse cotangent of some positive ratio we know would spit out an angle in quadrant 1. The answer to this is some quadrant 1 angle. Okay, so this is saying that the cotangent of some quadrant 1 angle has a cotangent ratio of 1/2, right? Well, we need to rewrite this as a cosine ratio. But that's a little bit difficult because it's not like you can just flip his over and now it's a cosine ratio. No, you're going to have to work a triangle to build a cosine ratio out of that cotangent ratio. So we need to rewrite as a cosine ratio. Okay, well, the good news is we already know it's a quadrant 1 angle. So we have an angle in quadrant 1. Drop yourself down. Here's the angle, perpendicular, and build yourself a right triangle. According to this angle has a cotangent ratio of 1/2. Cotangent is A over O. So we know A is 1, and we know O is 2, right? His adjacent side is 1, his opposite side is 2. I'm going to figure out this third side, and then I'm going to find what the cosine of this angle is. I need a cosine ratio. So a little Pythagorean theorem. 1 squared plus 2 squared equals c squared. That's 5. Square rooted, it's root 5, right? And in quadrant 1, this should be positive, this should be positive, and this is always positive. All right, so guys, get your cosine. The cosine of this quadrant 1 angle is what ratio? Cosine is A over H, right? So it's 1 over root 5. Don't even clean it up because we're not leaving it as our answer. So now I can find out what angle this is by taking the inverse cosine of this ratio that we just built. So take the inverse cosine of 1 over root 5, and you'll get the answer that this angle will be. So take the inverse cosine of 1 divided by root 5, get out of there, close catapult, and it is 1.11 radians. So the answer is the quadrant 1 angle that this is an answer to is 1.11 radians. And does 1.11 radians fall in quadrant 1? Yeah, he's an angle between 0 and 1.57 radians. So that is definitely the answer. Okay, let me give you a little bit of a spoiler. We had to rewrite the inverse cotangent as an inverse cosine because they both spit out angles in 1 and 2. However, we had already agreed that the inverse cotangent of 1/2 was a quadrant 1 angle, right? The inverse tangent is capable of spitting out quadrant 1 angles, right? So could I technically have cheated the system and turned this one into an inverse tangent and just said the inverse tangent of his reciprocal would get me the answer? Well, because we already knew the answer was a quadrant 1 angle and he can spit out a quadrant 1 angle, yes, you technically could have turned this one into an into an inverse tangent problem. Watch this. The inverse tangent of that reciprocal, which is 2, is what? What is the inverse tangent of 2? It's 1.11 radians, right? It gets you the same answer that we said is the angle. So technically, because it was a quadrant 1 angle that this inverse cotangent was going to spit out, and the inverse tangent can also spit out quadrant 1 angles, then yes, you technically could have turned this into an inverse tangent. All right, but I don't want you to get into that habit because if you were taking the inverse cotangent of a negative ratio, we know the answer would have been a quadrant 2 angle, and the inverse tangent can't spit out quadrant 2 angles. So it's really the ones where you take the inverse cotangent of a negative ratio that absolutely have to be turned into the inverse cosine. All right, so again, could you cheat this problem? Yes, but I don't want you to get into that habit. I want you to get into the habit of realizing that the inverse cotangent has to become the inverse cosine to be technically correct. okay? But yes, this one could have been cheated. All right, let's try this one because this one you cannot cheat. You have to go to the inverse cosine. Okay, well, the inverse cotangent of this negative ratio, right? Well, we know the inverse cotangent can only spit out angles in quadrant 1 or quadrant 2, angles between 0 and pi, right? Okay, we know if you take the inverse cotangent of a negative ratio, it's going to spit out a quadrant 2 angle. We know the answer to this is some quadrant 2 angle. Okay. So let's figure this out. So if we turn this around, this is saying that the cotangent of some quadrant 2 angle equals this ratio negative 2/3. Well, we need to turn this into a cosine ratio because only the inverse cosine, which is the one we have a button for on our calculator, can spit out the angle in quadrant 2. So rewrite as a cosine ratio, which means we're going to have to build a triangle and work that triangle and build ourselves a cosine ratio. All right, let me just get myself a better picture here because I'm going to get cut off. All right, so we have a quadrant 2 angle, all right, but we end up using his reference angle, like always, to build that right triangle. All right, well, we know the cotangent of this quadrant 2 angle has this ratio. Cotangent is A over O. So A is 2 and O is 3 off of this angle. Okay, which one gets the negative sign? Well, if you're in quadrant 2, you went left and up, so only the 2 should be negative. So he gets the negative sign from that ratio. All right, a little Pythagorean theorem. A squared plus B squared equals C squared. 4 plus 9 is 13. Square root it. That's root 13, and he's always positive. So find yourself the cosine of this quadrant 2 angle now. So the cosine of this quadrant 2 angle is equal to, well, cosine is A over H, negative 2 over root 13. And you don't even have to fix it. Don't even rationalize it. Just leave it. So now to figure out what angle this is, I have to find the inverse cosine of it. So take the inverse cosine of this ratio, negative 2 over root 13, and it'll tell us exactly what quadrant 2 angle we are working with. All right, so the inverse cosine of negative 2 divided by root 13, get out of there, close catapult, hit enter, it is 2.16 radians. That is your angle that makes this statement true. All right, and is 2.16 radians a quadrant 2 angle? Yeah, because guess what? This is pi over 2, so this is 1.57 radians, and this is pi radians, which is 3.14. So is 2.16 in between 1.57 and 3.14? Yes, it is. That is a quadrant 2 angle in radian measurement. All right, perfect. All right. So again, this one definitely had to go to the inverse cosine because the inverse tangent never would have spit out a quadrant 2 angle. And we knew this had to be a quadrant 2 angle. All right, last one. The inverse cotangent of negative 2. All right, well, we know if the inverse cotangent can only spit out angles between 0 and pi, quadrant 1 or quadrant 2 angles. So we know if you take the inverse cotangent of a negative ratio, that's a quadrant 2 angle. We know the answer to this is a quadrant 2 angle. But what quadrant 2 angle? All right, let's turn this around. This is saying that the cotangent of some quadrant 2 angle has a ratio of negative 2, or negative 2 over 1 if you want to see it as a fraction. All right, so now we have to rewrite this as a cosine ratio. All right, in order to rewrite this as a cosine ratio, we're going to have to work the triangle. So we have an angle that landed in quadrant 2. Okay. All right, we're going to use his reference angle to build the right triangle. This is saying that the cotangent of this quadrant 2 angle is negative 2 over 1. Well, the cotangent ratio is A over O, right? So according to this angle, A is 2 and O is 1. Who gets the negative sign? Well, left and up, this should be the negative number, so the negative 2, right? Well, now we need this side. So Pythagorean theorem, 4 plus 1 is 5. We square root it. It's root 5, and that number is always positive. All right, so get a cosine ratio. So right now, the cosine of this quadrant 2 angle is equal to A over H, negative 2 over root 5. So in order to figure out what angle this is, take the inverse cosine of that ratio. So the inverse cosine of negative 2 over root 5 is equal to what quadrant 2 angle? Well, let's find out. All right, the inverse cosine of -2 divided by root 5. Get out of there, close it, hit enter. It is 2.68 radians. Okay, and is 2.68 radians a quadrant 2 angle? Absolutely, because this is 1.57 radians and this is 3.14, and 2.68 is definitely in between them. Okay, all right, guys, that's the end of section 2. Please reach out to me if you are having any trouble, because these inverses can be a little tricky. Just remember how they work. What angles is each inverse capable of spitting out? Okay? All right, good luck on your homework. And again, I hope AP testing is going well.